What is going on, everybody? Welcome back to the blackboard. Yeah! Today we're going to be doing a kind of mixed lesson between ODEs and PDEs. This is going to be going in the ODE section of the differential equation page, but we are going to have some PDE examples, but you'll see what's going to happen. So, this video will cover two more ODE techniques. One of them is double substitution called like UV substitution. So pretty much you just let y equal to u x v x, where like y is y of x, and then you substitute it into the ODE, and then you just get some beautiful solution and a bunch of other stuff. But I will skip the whole like derivation and then just give you the format of the ODE and then what the solution is. As you can tell by my voice, it's very crusty because I'm recording the same day as the time independent solution one. But yeah, let's get started. So for this one, we are going to be given in second order ODE in the form of y double prime of x plus p of x times y prime of x plus q of x y of x equal to 0. So yes, this ODE must be homogeneous, meaning this has to equal to 0. And so what we can do is there is a solution to this ODE in which we can express y of x being equal to u of x, where like I mentioned, like the whole double substitution. So u of x multiplied by e and have that raised to the negative 1/2 times the integral of p of x dx. So as you can see, p of x and q of x must be functions of x, or just functions in general. If they were both constants, then you just have constant coefficients, so you can just use the table from the cheat sheet series or whatever method that you desire. But we know what p of x is, but what is u of x? Well, u of x is a second order linear homogeneous ODE that satisfies the ODE u double prime of x plus r of x times u of x equaling to 0. As you can see, now we have another variable, r of x. Again, that is a function as well, but two things to note. U prime of x is equal to 0 here. Let me actually make this thicker. So u prime of x is equal to 0 here. And the second thing, which is like a special condition, if r of x is equal to a constant, then the ODE is a constant coefficient ODE that you can solve, like I mentioned in the previous one, using the table or like method of characteristics or whatever floats your boat. So now this begs the question, what is r of x equal to? Well, I'll tell you this. R of x is equal to, this is where it gets annoying. This is equal to q of x minus 1/4 p of x, but that p of x is squared, minus 1/2 p prime of x. And so again, if you plug in the q of x and p of x and its derivative, if that's equal to 0, then we have this special case where the ODE is a constant coefficient and we can just solve it like regularly. So we're going to do an example. Obviously this example is going to contain the beautiful condition here, But if it doesn't, then there are other ways to solve this ODE. Like I mentioned, ODEs is pretty much guessing how to solve it. So yeah, we're gonna go ahead and do an example, and it's gonna use this method thing. So this example tells us to find the time-independent solution to the PDE as shown here for x that's between 1 and 2 and t greater than 0, along with the boundary conditions of u of 1t is equal to 1 and u of 2t equal to 0 for time is greater than 0. Like I mentioned, this is like a PDE, but don't you worry, everything's gonna be okay. If you are here from the time independent solution video, you know what that is, and so we're gonna go ahead and solve it. But before we solve it / find it, like I mentioned in the video, you must always check if such solution does exist and if it's really like necessary to find it. And so we are gonna we're gonna check the conditions. Obviously the most easiest one is looking at the boundary conditions, and as we can see, we have u of 1t equaling to 1, which this is not equal to 0, therefore this is non-homogeneous, and so a time-independent solution, which we're going to call ue to the x, could exist. It's not always guaranteed, but for the sake of this example, this will actually exist. And so once we get that out of the way, we now must explicitly state that we're going to let ue to the x, or uxt, be equal to ue to the x. And so when we substitute this, we are going to have x times d ue to the x, that's second derivative because of the x squared at the bottom, dx squared plus 2 times the partial derivative due to the x, all over, wrong color, dx plus x times ue to the x, and that is equal to d ue to the x, or the partial derivative of ue to the x with respect to time. And so now we're going to do a little bit more simplification. Oh wait, don't forget the boundary conditions now become ue to the 1 is equal to 1 and ue to the 2 is equal to 0. And so now we're going to simplify this, and notice that the function that we're taking the derivative of on pretty much the left side, so here, here, and here, well, this one doesn't really count because it's not a derivative. We can see that we're taking the derivative of one variable on a function that has that one variable, and so we can just simplify this as x times ue double prime of x plus 2 ue of x plus x ue of x. And then on the right side, it's the same thing. You're taking a derivative of one variable with respect to a function that has one variable. The only difference is we are taking the derivative with respect to a variable that's not in the function, and so that will just become a constant, or we can treat it as a constant, and therefore the right side would just be 0. And so here you have a regular ODE. The only issue is not the constants, but the things in front of everything else. This is supposed to be an x. Looks kind of wonky. For starters, we typically don't like having something in front of the second derivative. And so what we're going to do now is we're going to divide everything by x, so we can get rid of the x. So we can divide everything by x, and so now we get UE double prime of x plus 2 over x. I guess I'll just do this one in the red color. 2 over x times UE to the x plus x over x is just be equal to 1. This one's prime. UE to the x is equal to 0. And so now we have a, I guess, cleaner or like better ODE than we had in the first place. I mean, it's still a little bit fishy, mostly because of the 2 over x. And so, like I mentioned, we're going to use the case that we discussed like a couple minutes ago. We are going to find what r of x is. And so we are going to just do that right now. So we're going to let r of x be equal to, well, actually, before we do that, let's actually define or like find what our p and q is. As you can see that this is going to be p of x. So this will just be 2 over x. And then q of x will be just 1 because there's the only thing in front of the UE to the x is just 1. This kind of looks janky. X, cool. And so now we're going to find what r of x is and hope that it gives us a constant so we can use that special case. And so like I mentioned, this is equal to q over q of x minus 1/4 p prime of x. No, not p prime of x. P of x quantity squared minus 1/2 p prime of x. And so this is going to be equal to 1 minus 1/4 times 2 over x quantity squared minus 1/2 times p prime. P prime is equal to negative 2 over x squared. And so when we do a little bit of simplification, we get 1 minus the 4's cancel, or the 4 and the 2 get reduced to 2 over x squared, or I guess 4 over x squared. Does it? No, because it'll be 2 squared, which would be 4, so there should be 1 over x squared. And then on the other side, the 1/2, the negatives get canceled to a positive, so we have, and then the 2's cancel out, and so we have plus 1 over x squared, and then we see that those 2 cancel out, and we're just left with 1, which is equal to a constant, which is equal to r, and therefore we can do the whole special condition. We already know what our solution is. Y of x is going to be equal to u of x times e to the negative 1/2 the integral of p of x dx. And so before we get, well, actually, yeah, this is going to be our solution. And it was just a matter of checking that like special case that just gives us a constant. So therefore we now have another second partial or second ODE that is u double prime of x times, not times, plus r of x u of x is equal to 0. We know that r of x is equal to 1, so this is equal to u double prime plus u is equal to 0. And so when we implement our, or we're going to use the table method to solve this, we see that alpha, well, actually d is going to be equal to 0 minus 4 times 1 times 1, which is equal to negative 4, so that'll be less than 0. So we have the first case on the table. Therefore our solution u of x is going to be equal to c1 cosine of, well, beta, well, actually alpha alpha is going to be equal to negative b over 2a. Because b is equal to 0, a, or alpha, is equal to 0, and then our beta is going to be equal to the square root of negative d, so it'll be the square root of 4, which is 2 over 2 times 1, which is just 2, so this will be reduced to 1. Therefore, our solution will be for u of x, will be c1 cosine of x plus c2 sine of x. Cool. And so now we are going to find what the e to the negative 1/2 times the integral p of x is. So this portion right here, and we're not going to do the raising power thing, we're just going to like do it separately. So negative 1/2 times p of x, I mentioned that that was 2 over x, so it'll be the integral of 2 over x dx, and so that will be equal to, the 2's cancel out, so you have negative multiplied by the integral of 1 over x dx, which, if you remember in integral calculus, that this is just equal to negative natural log of x, or just natural log of x raised to negative 1/2 if we use the log rules. And then when we substitute it in, we will get that this is e to the natural log of x to the negative 1, or the e and the natural log cancel out, or it gets reduced, leaving us with 1 over x, giving us our solution to the time-independent solution, u e to the x, being equal to c1 cosine of x plus c2 sine of x, all multiplied by 1 over x. And so that is our time-independent solution, but we are not done, because we have the condition u of 1 is equal to 0. No, u of 1 is equal to 1. Let me fact check this. U of 1 is equal to 1 and u of 2 is equal to 0. And yeah, u of 2 is equal to 0. So now we're going to plug this in, and so this is ue. Apologize. So the boundary conditions, let's use green. If we let u of 1 and substitute it in, we will get 1 over 1 multiplied by c1 cosine of 1 plus c2 sine of 1, and then ue of 2, and then this is going to be equal to 1. Then u of 2 will be 1/2 times c1 cosine of 2 plus c2 sine of 2, and this is equal to 0. And so the way you can solve this is you can use matrices, you can use systems of equation. I'm going to use matrices and then like skip steps. So we're going to put this in a matrix, and this is pretty much equal to cosine of 1, sine of 1, 1/2 cosine of 2, and 1/2 sine of 2, because I'm distributing the 1/2 in this portion here, and that is multiplied by c1 and c2, and that is equal to 1, 0. And so what we do here is that we're going to multiply both sides by the inverse of this 2 by 2 matrix. So both sides are going to be multiplied by cosine of 1, 1/2 cosine of 2, sine of 1, then 1/2 sine of 2, negative 1/2, and like both sides. And so when we do that, we get that c2, or I guess c1 and c2 will be equal to, actually the thing will factor out if I'm correct, 1 over sine 1 multiplied by sine of 2 and negative cosine of 2. And so when we plug it into our final solution, our actual time independent solution will be equal to, or will be UE to the x, and that will be equal to C1 will be 1 over x all multiplied by sine of 2 over sine of 1 times cosine of x plus minus, because of the negative, so this will be minus cosine of 2 sine of 1 times sine of x, and that is our time independent solution. So that'll be it for this video. I'm gonna make a second part that talks about the other ODE method. I'm already like over 20 minutes, so I'm gonna stop it here, and then I will see you guys in the next video.